So I want you to imagine a massive military cargo plane.
Okay.
It's touching down on this entirely dark, unpaved runway in like a completely hostile environment.
Right. Total blackout condition. Yeah.
Exactly. And the rear ramp drops heavily into the dirt. But instead of unloading, a massive platoon of heavily armored soldiers or a fleet of rolling tanks, the ground crew pulls out what essentially looks like a packed-up metal puzzle.
A very dense metal puzzle.
Yeah. It's compact, it's folded in on itself, and it looks completely dormant. But less than 7 minutes later, that puzzle has been unfolded, locked into place, and is literally a fully armed, flight-ready attack helicopter.
And it's lifting off into the night sky before the enemy even knows you've arrived.
Exactly. Today, we were looking at the Boeing AH-6 Little Bird.
It's a profoundly counterintuitive machine, because when we study military aerospace engineering, the historical trend is almost always like, if you want more capability, you just add mass.
Right, you build a flying warehouse.
Yeah, exactly. If you want something tougher, more lethal, more versatile, you just make it bigger. But the AH-6 completely rejects that premise.
And that is exactly our mission for this deep dive.
Yeah.
We are looking at the official product and capabilities documents from Boeing to unpack how this incredibly specific rotorcraft manages to fit heavy-duty multi-mission capabilities into a footprint so light and adaptable, it almost seems like a contradiction in physics.
It really does.
So whether you are, an aviation enthusiast analyzing flight specs, a software developer looking at systems architecture, or just someone trying to figure out how to do more with fewer resources, we are going to see how extreme physical constraints actually force the most innovative design solutions.
I love that framing.
So I've got the documentation right here. Okay, let's unpack this.
Well, the best place to start is with the fundamental identity of the aircraft, which the source material defines by its sheer versatility. Boeing categorizes the AH-6 as a light attack and multi-mission helicopter. But I have to say, in military aviation, multi-mission is usually kind of a dangerous word.
Oh, really? Why is that?
Because historically, when you try to make an aircraft do everything, it ends up doing nothing particularly well. I mean, it becomes bloated.
I was actually just thinking about that.
Nah.
Because usually, highly specialized tools are incredibly rigid. Right?
Ironically.
Like a sniper rifle is terrible at close quarters combat, or, a sledgehammer makes a really lousy scalpel.
That's a great way to put it.
But I'm looking at the documentation here, and it lists the AH-6's operations. And honestly, it reads like the resume of an entire fleet of different highly specialized aircraft.
Yeah, the list is staggering.
It says it's built for precision, day and night engagement, anti-armor operations, close combat attack, reconnaissance, security and escort missions, troop insertion and extraction, and even combat search and rescue.
It's a lot.
How do you cram all those conflicting operational profiles into one single lightweight frame?
You do it through a physical architecture that is built entirely around rapid reconfiguration.
Okay, meaning what exactly?
Meaning the engineering challenge isn't just making the helicopter capable of shooting an anti-armor missile. It's making the helicopter capable of stripping off that heavy weapons system and pivoting to, like, a delicate search and rescue operation in a matter of minutes.
Oh, wow. Which brings us right back to that opening scenario, right? And a specific feature in these documents called blade fold capability.
Yes, that is crucial.
The text explicitly states that ground crews can transition the AH-6 from a packed-up transport configuration into a fully flight-ready configuration in under 7 minutes.
Under 7 minutes. Think about that. What's fascinating here is the operational reality that a 7-minute setup actually creates on the ground.
Right.
Because in high-tempo military operations, time isn't just, a metric you put on a spreadsheet. Time is literally survival.
Yeah, every second counts.
Exactly. When you fly into a forward operating base, your arrival is often the most vulnerable moment of the entire mission. Because you are static.
You're a sitting duck.
Precisely. If it takes your engineering team 2 days, or heck, even 2 hours, to reassemble your air support, you have handed the initiative entirely over to the enemy.
Yeah, they know exactly where you are and what you're doing.
Right. So a 7-minute setup fundamentally changes the pace at which teams can operate. It provides what Boeing calls in the text a persistent presence and rapid response.
I like that phrase, persistent presence.
Because you aren't telegraphing your moves days in advance. You arrive, you unfold, and you dictate the terms of the engagement.
It's less like that old cliche of a Swiss Army knife,
Yeah.
where you just pull out a different, highly compromised little tool.
Right, the tiny scissors that don't actually cut anything.
Exactly. It's more like a high-end modular camera rig.
Oh, that's an interesting comparison.
Yeah, so you have this core sensor and power unit, right? But depending on whether you're shooting a fast-action sporting event or a really dark, moody indoor scene, you snap on a completely different lens, battery pack, and stabilization gimbal in minutes.
That is a highly accurate way to visualize it. The modularity is the weapon.
Right. It's incredibly complex, but it isn't rigid.
But that modularity introduces a massive engineering paradox.
Because you can't just snap a helicopter together like a piece of modular IKEA furniture in under 7 minutes and expect it to survive a combat zone.
Exactly. If it's designed to be easily taken apart, the natural assumption is that it's inherently fragile.
Right. So how does a light helicopter actually perform heavy lifting without, rattling itself to pieces the moment someone shoots at it?
Well, to answer that, we have to look at the helicopter's genetic code, so to speak.
Okay, it's DNA.
Yeah. The AH-6 didn't just emerge from a vacuum. The documents emphasize that it is derived from more than 30 years of combat-proven evolution from another Boeing platform, the AH-64 Apache.
Oh, wow. And for you listening, if you aren't a massive aviation buff, the Apache is an absolute beast.
It really is.
I mean, it is essentially a flying tank.
Mhm.
It is the gold standard for heavy, lethal attack helicopters.
Exactly. So the engineers essentially took 3 decades of heavy Apache DNA and ported it into this highly agile, lightweight frame.
That sounds like a cheat code.
It kind of is. The Boeing specs list a fully integrated digital glass cockpit, an advanced mission computer, and the latest software, all directly inherited from that Apache evolution.
Let's pause on the concept of the glass cockpit for a second.
Good idea, because it is critical to how the aircraft functions.
Right.
So, in an older analog helicopter, the pilot is surrounded by dozens of physical dials, gauges, and switches.
Like flying a museum piece.
Exactly. And flying the aircraft requires a massive amount of manual cognitive load. The pilot is constantly scanning all these analog instruments just to keep the machine in the air.
Leaving very little mental bandwidth for the actual tactical mission. So a glass cockpit basically replaces all that physical clutter with integrated digital displays.
Yes, and more importantly, it utilizes an advanced mission computer to process millions of data points. And then it only presents the pilot with exactly what they need to know at that exact second.
Oh, so it curates the information.
Right. It takes the processing power of a massive heavy attack helicopter and gives it to a pilot flying a machine a fraction of the size.
That's wild. But I mean, the processing power still has to translate into physical movement, right?
Of course.
And here's where it gets really interesting for me. Because I'm looking at the raw performance numbers in the source material, and they seem completely at odds with the idea of a lightweight modular frame.
The numbers are pretty shocking.
They really are. We are talking about a maximum cruise speed of 126 knots, a maximum range of 179 nautical miles.
Which is substantial for its size.
Yeah, it has a maximum endurance of 2.1 hours. But the number that honestly stops me in my tracks is the climb rate.
Yeah.
It can climb at 2,162 feet per minute, up to a maximum service ceiling of 20,000 feet.
Those numbers represent a staggering amount of kinetic energy.
Exactly. I mean, for a helicopter, climbing at over 2,100 feet per minute is like a rocket launch.
It's aggressive, to say the least.
To get a rotorcraft to shoot straight up that fast, you are fighting incredible aerodynamic drag and obviously gravitational pull.
Not to mention the torque.
Right. The torque generated by the main rotor trying to rip the fuselage in the opposite direction must be immense.
It's massive.
So how does a light platform carry weapons, advanced sensors, a human crew, and still overpower the atmosphere like that?
It all comes down to a crucial engineering principle highlighted in the Boeing documentation. They call it an unmatched power-to-weight ratio.
Okay, power to weight.
Yeah. In aerospace engineering, literally every single rivet and wire is a brutal trade-off between the power your engine generates and the mass you have to lift.
Because every ounce counts.
Exactly. Because the AH-6 is so remarkably light, its engines provide a highly disproportionate amount of power.
Okay, I follow.
And that excess power is what allows for 2 very specific, highly dangerous types of flying mentioned in the source material. High hot performance and nap of the earth flying.
Oh man, I want to dig into the physics of both of those because they sound like absolute nightmares for an aircraft.
They usually are.
Let's start with high hot. What does that actually mean?
Well, when you fly at high altitudes, like approaching that 20,000-foot ceiling we mentioned, Or when you fly in very hot climates like a desert environment, the air physically changes.
Right, it gets thinner.
Yes, it becomes thinner, meaning it is less dense. And for a helicopter, thin air is the ultimate enemy.
Why is that?
Because a helicopter flies by using its rotor blades to physically push down on the air beneath it. If the air is thin, the blades have less mass to bite into to generate lift.
That makes sense.
Simultaneously, the engines have less ambient oxygen to burn to create combustion.
Oh, wow. So the aircraft is essentially suffocating while losing its grip on the sky.
That is exactly what happens to most heavy helicopters. They struggle massively in high, hot environments.
Because they're just too heavy.
Right. Their heavy armor and massive payloads become severe liabilities because the engines simply cannot generate enough lift in the thin air to carry the mass.
But the little bird is different.
Yes, because the AH-6 has such a superior power-to-weight ratio, it has excess power in reserve.
Ah, so it just muscles through it.
Exactly. It can aggressively power through that thin air, maintaining operational flexibility in theaters where heavier machines are completely grounded.
That makes total sense. It's just overpowering the environment.
Right.
But what about nap of the Earth flying? Because that sounds less about the atmosphere and more about the terrain.
It is. Nap of the Earth flying is a highly specialized tactical maneuver where the pilot flies as close to the physical ground as aerodynamic laws will basically allow.
Wait, how close are we talking?
We are talking about hugging the terrain, dipping down into river valleys, and flying strictly below the tree line.
I'm trying to visualize this. Flying at 126 knots, which is, what, about 145 miles an hour?
Roughly, yeah.
Inches above a tree line or a rocky ravine, especially at night. I mean, that sounds less like tactical flying and more like a highly controlled crash waiting to happen.
It is incredibly intense.
Your margin for error is essentially zero, like a misjudged branch or a sudden gust of wind, and you are into the dirt.
Exactly.
So is it just the pilot's raw physical skill keeping them alive down there, or is that Apache software taking over?
It is really the synthesis of both.
Okay.
To fly nap of the Earth safely, you need an aircraft that responds instantaneously to the pilot's physical inputs. Heavy lumbering machines have inertia, they're sluggish.
Yeah, they can't turn on a dime.
Right. When a pilot pulls the cyclic to dodge an obstacle, a heavy machine takes a fraction of a second to respond.
And at 145 miles an hour?
At 145 miles an hour, that fraction of a second is fatal. The AH-6 has the lightweight physical responsiveness required to dodge obstacles, combined with the integrated Apache sensor technology like forward-looking infrared.
So they can see in the dark.
Exactly. So the pilot can process what is hidden in the dark ahead of them fast enough to actually react.
But, that leads us directly into a massive tension in the design.
How so?
Well, you are threading a needle at over 100 miles an hour, inches above the ground, in an aircraft that we've already established is inherently lightweight.
Yes.
If they stripped away the massive steel armor plating to achieve that incredible power-to-weight ratio and agility, what happens to the human beings inside when things inevitably go wrong?
That is the big question.
Because a bird strike or a mechanical failure at that altitude means you are hitting the ground instantly.
It does. And that brings us to the next crucial section of the document's survivability.
Right.
Because you cannot put a human crew in that extreme of a kinetic environment without a comprehensive way to protect them.
So what do they do?
Well, the documentation points out that the AH-6 features a purpose-built military-grade fuselage.
But they don't just mean thick armor, right? Because as you said earlier, adding thick steel ruins the very agility that makes the helicopter effective in the first place.
Exactly. You can't just wrap it in a steel box. The text specifically describes a systems approach to crew protection and crash survivability.
A systems approach.
Yes. If we connect this to the bigger picture, survivability in modern aerospace engineering is essentially a study in kinetic energy management.
Okay, kinetic energy management. Break that down for me.
When a helicopter experiences a hard landing or a crash, a massive amount of kinetic energy is generated, right?
Yeah, obviously.
If the aircraft frame is perfectly rigid, like a solid block of steel, all of that violent energy transfers directly through the floorboards and straight into the pilot's internal organs.
Oh, wow. That sounds horrific.
It is. It's lethal.
So when I see the phrase systems approach and crash attenuating seats in the source material, my mind immediately goes to the crumple zones in my car.
That's a really good analogy.
But, a car hits a wall on a flat two-dimensional road. The hood crumples, the airbags deploy. A helicopter crash is a three-dimensional, high-velocity vertical drop.
True.
You can't exactly put a 6-foot crumple zone underneath the pilot seat, can you?
Actually, you can, But it is engineered through stroke mechanics, not just crushing metal.
Stroke mechanics.
Yeah. The text gives us the exact components of this sequential system. It lists energy-absorbing landing gear, a robust airframe structure, those crash-attenuating seats, and advanced restraints designed to reduce occupant loads.
Okay, so how does that sequence actually bleed off the energy during a vertical drop? Walk me through it.
It happens in fractions of a second. First, the energy-absorbing landing gear makes contact with the ground.
Right.
Instead of being rigid struts, they are designed to collapse and stroke at a very specific rate, acting like massive shock absorbers to eat that initial spike of kinetic energy.
Okay, so the gear takes the first hit. Then what?
Next, the robust airframe is engineered to flex slightly, but ultimately maintain the survival space.
Meaning it doesn't crush the pilot?
Exactly. It prevents the cabin geometry from crushing inward and trapping the crew.
And the seats, where do they come in?
That is the final, most brilliant line of defense.
I'm intrigued.
Rather than bolting the seats rigidly to the floorboards, which again would still transfer lethal G-forces to the pilot's spine, crash-attenuating seats are mounted on rails.
Oh, wow, on rails.
Yeah. During a severe impact, the seats are designed to literally stroke or slide downward in a highly controlled, resistant manner.
So the seat itself absorbs the shock.
Right. They absorb the remaining kinetic energy over a few crucial inches of travel, so the human spine doesn't have to. The entire machine is basically a continuous energy dissipation system.
That is incredible engineering. So it's protecting the most valuable asset, the crew, physically.
Yes, absolutely.
But there is another kind of survival that the Boeing documents focus heavily on.
Which is,
So what does this all mean for the survival of the actual program itself?
I see where you're going.
Because the greatest, most capable energy-dissipating machine in the world is completely useless if you can't afford to fix it.
All right.
Or if it's constantly sitting broken down in a hangar just waiting on parts.
You are hitting on logistics.
Yeah.
It is the unglamorous, often overlooked, but absolutely vital backbone of any military or enterprise operation.
Right. Think about the last time your personal car broke down and the mechanic called you to say they had to order a bespoke, custom part from an overseas manufacturer.
It's the worst.
You were probably grounded without a vehicle for weeks.
At least.
Now imagine that exact same scenario happening, but you are in a combat zone and the vehicle is your air support.
That's a terrifying thought.
That's why the source material emphasizes comprehensive sustainment and logistics solutions to maximize global fleet readiness.
Boeing specifically highlights how they lowered the sustainment burden and reduced the total ownership cost.
Right. And the mechanism they use to achieve this is commonality with existing rotorcraft infrastructure.
Yes.
By commonality, they mean leveraging the Apache lineage again, right? Like sharing physical parts.
Precisely. If you design a completely bespoke helicopter where every single rotor actuator, computer chip, and hydraulic valve is entirely unique to that one airframe, your supply chain becomes a fragile nightmare.
Too complex to maintain.
Exactly. By designing the AH-6 to share parts, maintenance procedures, and support services with the existing massive global fleet of Apache helicopters, you ensure that spare parts are already sitting in the logistics pipeline all over the world.
Oh, that's brilliant. So if a part breaks at a remote forward operating base, the mechanic doesn't have to order a custom AH-6 part and wait weeks for it to arrive.
Nope.
They just walk over to the existing supply tent, grab a component that also fits the heavy attack helicopters, and the little bird is flying again in an hour.
Exactly. And Boeing notes they offer options from simple transactional spares all the way to full performance-based logistics.
Meaning they handle the whole life cycle.
Right, handling integrated fleet support, maintenance, and modifications.
Yeah.
It proves a much larger point about design, really.
Which is?
That endurance isn't just about having a fuel tank that lets you fly for 2.1 hours.
Right.
True endurance is about having a resilient supply chain that ensures the aircraft is physically capable of flying that 2.1 hours every single time you turn the key, no matter where you are on the planet.
It's minimizing the footprint, not just physically with the folding blades, but logistically with the supply chain.
Exactly.
Which really brings this entire analysis full circle. For you listening, this is exactly why the AH-6 Little Bird is so much more than just a fascinating piece of military hardware to geek out over.
It really is.
It is an absolute masterclass in adaptive design and extreme efficiency. We started this deep dive talking about how our default assumption is that bigger is always better. You know,
right.
How we expect heavy-duty tasks to require massive lumbering machines. But this rotorcraft just completely shatters that assumption.
It turns it on its head.
Whether you are managing a complex business pivot, designing software architecture, or honestly just trying to pack for a highly complicated international trip, the AH-6 proves a universal truth.
Which is?
Minimizing your footprint while maximizing your capabilities isn't a limitation. It is the ultimate strategic advantage.
And that raises an important question to leave you with today. Think about that AH-6 blade fold capability and its under 7-minute rapid configuration.
Yeah.
In a modern world where economic conditions, technology, and environments change almost instantly, and adaptability is literally everything, what is the blade fold capability in your own life or career?
That's a great question.
How quickly can you pack up your current systems, pivot to a new environment, and launch a completely new strategy before the competition even knows what's happening?